thank you for joining in this webinar here today. What I will talk about here is a quick introduction to the new release of our software, MCalibration and PolyUMod. This is release 6. So there are some new changes into the installation and the file structure of the new release that I think are useful to know about. So I'm going to talk about that first before we get into the new features. First, if you're interested in all the new features and what they're looking like, there are a few different ways in which you can determine what the changes are. There's a changelog that you can look into. So what I will try to do is I will try to demonstrate that here. So there are two key ways you can get to that. So the one easy way is if you open the new version of MCalibration, you get a window like this. And then if you go to the Help menu and then just View Changelog, you should see a web page pop up that contains all the details, new version. So here is that. So that's an easy way to get to the changelog. The next thing I want to talk about is that the new release comes with 2 installers. In our previous release, there was one unified installer for both MCalibration and PolyUMod. Now we have 2 installers, one for MCalibration and one for PolyUMod. And once you install the software, you will have a different file structure on your computer. So I can quickly show you what the structure looks like here. So to demonstrate that, I will open up our support website. So PolymerFEM.com is our general website. You just click on support in the menu bar. And then for Windows installation guide, if you click on that icon, then you can see the description of how to install the software for a Windows computer. It's I think it's more streamlined than the previous release. You have options of what kind of license file you have, or an activation key, and these are the instructions for how to install the software and walk through that. And it looks very similar for PolyUMod. The end portion here is somewhat important too. The software uses a few different environment variables that are set by the installer, but it's good to know what they are. There is one main license environment variable called RLM license. This used to be called various license, and this is a variable that points to the license server, typically 5053 at localhost if you have the license server running on your own computer. If you're an Ansys user, you should also have an environment variable called ans user path set. This should point to the PolyUMod version for Ansys, and you can see the path here for a Windows computer. And similarly, one of the new features that I will mention in a little bit, we also support now Altair Radioss. So there is an environment variable for that called rad user lib path. So those are the environment variables that should be set for you. But if you want to check that, you can check that they are indeed set for you. I'm going to open another folder here and take a look at the file structure that we're working with. So I'm going to go to my C drive, program files. PolymerFEM is where things sits now. In MCalibration, we have the MCalibration files. The actual executable is this one. So if you double click on that, you will open MCalibration. The PolyUMod files are in this folder. There is a license folder here that contains the license file. It should sit in this directory, and the installer will put that for you in that location. And then there is a PolyUMod folder for each FE solver that we support. So for Abaqus, there is these 3 DLL files that Abaqus will use when it calculates stresses at each integration point. And there is an example environment file that needs to be set up for Abaqus to work properly. This is something that the installer also will do for you. If you let it to, they will ask you if that's something you want to do. If you want to read more about that too, that's also part of one of our help documents here under support. If you go to PolyUMod installation for Abaqus, then I will talk a little bit about this files format here. So you can take a look at that if you need to change that. for you. But the installer should take care of all of that, typically. And that's really all I want to say about the installation and the file folder structure. The one thing that not everyone is aware about, know about, is the license server. PolyUMod is typically served through a network license. So you can quickly check the status of your network license by going to a web page. So in this case, I'm running the license server on my laptop here. And the the address I want to go to is localhost:5053. 54, I think it is. 54. And that gives a web page that the license server shows for you. So if you want to know if your license server is working properly, what's going on, how many licenses are in use, I will go to this web page, localhost:5053, and replace localhost if you're running the license server somewhere else. And click on status, and then under server status, you click on that button, and you should be able to see somehow it's a little slow today. Let's see if it's coming. It should show you here we get the table of licenses that I have on my computer. So on your computer, you should see something similar. What products you have a license for, how many of licenses are in use, and things like that. So that's very handy if you're looking at license issues as you work on things. So that's my little introduction about the file structure. Let's talk about new features in PolyUMod first. So we are supporting these versions of the FE solvers, as you can read on the screen here. The new one is Altair Radioss. That's available today. When you're using Altair products, as some of you know, they have their own licensing system typically. So we will support Radioss in two ways, either by a PolyUMod license that you get from us, or you can also get it through your Altair license, hardware license that comes from Altair. But the integration into the Altair license system will not happen until the next Altair release, which is the beginning of 2021. But you can still use it today using a PolyUMod license for Radioss, if that's something you're interested in. So those are some of the features for PolyUMod. Let me do a quick little demonstration for Radioss. So I have a test case here. Let me just show the directory structure again. So on the C drive, program files, PolymerFEM, and PolyUMod, I have test cases. We have test cases for all of these solvers. So under Abaqus, if you're interested in Abaqus, these are the test cases that you can run to see if it's been installed properly. And there is a BAT file here that we provide that basically runs it for you. So here's the command Abaqus. This one uses hotfix 5, and it runs a very simple test case that you can try. Now, what I wanted to demonstrate here is the Radioss solver. So let's take these files and very quickly run them. I already copied them over to my demonstration folder here, test cases Radioss, and then I just click run simulation, and it launches Radioss just like it runs and launches any other finite element solver. It's running it in the background, and this takes like a few seconds to run. While it's running, we can quickly look at the command that was used to start this calculation. It looks similar to most other things. You set up a call to the executable, to say how many processors you want to use, and then an input file. So nothing surprising there, even if you're not familiar with that particular explicit solver. Instead of waiting for this and pulling it up live, I saved a screenshot what the results would look like, and that's the next slide, as you can see here. It is basically us sharing some cylinder, but the point is that this is now available. You can use, if you're a Radioss user, you can use all the PolyUMod material models, which will give you more accurate predictions than many of the built-in features. Now, I want to spend most of the time left here talking about MCalibration and some of the new features that we have. There's some GUI improvements. So if I open the interface, you'll see that has a little bit different labeling and structure to it. But the functionality is pretty much exactly the same, plus new features. So as before, if you want to read the manual for the software, you can click on PolyUMod manual. It opens a PDF file that describes all the PolyUMod material models. That can be handy sometimes. If you want to get some online help, this button opens a web page. And here it is. This is the one we looked at before. So those are sometimes handy to take a look at. And that's some of the GUI features that are new here. There's some improvements in copy and paste that you may find silly, but it actually makes things much quicker many times. So if you open a file that you have working on, say this file, and you want to copy. So those of you who haven't used MCalibration too much, the experimental data is in the top left, the material models in the bottom left, and then the predictions are on the figure there. So if I say I want to copy these experimental tests here, I can just select them and type Control, clicking on copy here, for example. I can open another MCalibration window, and then I just type Control V with my keyboard, and it pastes the load cases in directly. If I want to copy this material model, I just copy it, and then I can just Control V, and I get it here. So you can copy features from one window to another very quickly, if that's something you're interested in. So Control V works very well now for most of those features. The other new feature or improvement in the GUI is that if you say you want to calibrate from this point, this happened to be a relatively good prediction. The blue lines are relatively similar to the red one here. But if you want to calibrate more, you run calibration, you'll see that there is a new section here that allow you from within this optimization portion directly specify how many CPUs you want to use, how long you want it to run, etc. Before, in the previous version, you had to specify that under preferences. Now you can do it directly here. So you keep that in mind as you start running some kind of calibration. So that's another interesting, useful thing. It makes it a little quicker. The last thing I want to mention about the GUI improvements is related to the graph window. In the graph window like this, it looks like it's a yellow background. Some people don't like that at all. So you can customize the background very quickly using some of these toolbars. You can right-click in this. But we have a new set of options here under the graph where you can save styles that you like. So now I have saved something original style. I can change it to something that I created called horizontal grid. I select this one and I apply this one. It changes the look of it. Now it's a bunch of horizontal line. Okay, maybe I like that, fine. I have saved another version of a graph style with a different font system. Maybe this is in the white background. So if someone gives you a MCal file that has fonts and backgrounds that you really don't like, then you can have your own defined and you can just apply them very quickly. And then you get them to look like you want in your own reports or whatever. So that can be quite handy. I find when I write all kinds of reports, I like to have consistent look of my figures, even if other people work on those figures. So that's the GUI. I want to talk a little bit about the new features. We have some really cool new features that are worth talking about here. I'm going to first demonstrate something called a data file merge. So if I go to my test cases here, this one we can actually close. We don't need that window. I'm going to close this one too. So I have a folder here. If I go to I go to my documents, temp, webinar, data file merge. So these are two data files that I want to merge together. So say you run, you run it or someone in your company run an experimental test. There may be a test where they provide you 3 columns. This is time. We have to read the comments here. Crosshead position and load. you can actually open this in MCalibration. It makes it a little easier to look at it. So I'm going to close this old window, open a new window, and then I'm going to go to data under the data tab so we can read in this data, this experimental data. So I'm going to load my data file. And then I'm going to have to navigate back to where I were. I'm going to go to webinar, data file merge, test machine data. So here's my data, time crosshead position load. So I can plot crosshead versus load. This is what some weird test, right? But say I also have data, I may have DIC data, digital image correlation, where I measure the strain optically. So that's typically in a different file. So I have one file with the force displacement and one file with the strain. So let's take a look at the DIC strain data. So I'm going to load another file just so we can look at it, this file. So here's the engineering strain versus time. It has a very different number of rows of data. They're not different, the different time points. But I want to merge these files. So I have one master file with time, strain, crosshead, and stress. And that's something we can do very quickly now in this new version. I'm going to read in my test machine data, and then I'm going to go to data, merge an external data file, and I select DIC, and I say open, and here it is. It merges the second file I read in. It interpolates the data points so that it matches the time points in the first file, and that gives me the ability to plot. Instead of crosshead displacement, which is typically less accurate, I can switch over to plot engineering strain versus load. So this is the actual strain in the specimen. So that's a handy thing if you have multiple sources of data and you want to just combine them. This is something you, of course, can do other ways, but this is just very simple and quick to do it with this new feature. So we like that. Another feature is the ability to work with multi-temperature models in the PolyUMod library. So this is a little bit more advanced, but it's worth mentioning. So I'm going to close this file. I'm going to go up a directory, and I'll talk about multi-temp model. So say you have material data at 2 different temperatures, or many temperatures, and you calibrate a material model for each temperature. So here is a rubber material. I used the Bergstrom Boyce model. This is a low temperature data, and here's some prediction. Okay, great. So then I can open my other file, T1, which is a high temperature prediction. And if we try to see both at the same time, we'll see that this low temperature has higher stress than at high temperature. Okay, great. These are now Bergstrom Boyce model. They happen to be PolyUMod versions of the Bergstrom Boyce model. Say you want to combine this into a single temperature dependent Bergstrom Boyce model. How would you do that? Well, you can always do that using a template material model. So I'll show you that. So I open a material model selection dialog box. I go to PolyUMod, and I go to PolyUMod template. And this is a new feature that allows me to combine multiple files into a multi-temperature model. So I click on this one. I select the material parameters I have already exported from these 2 individual tests or calibrations. I open them, and it generates this file. This is what's called a multi-temperature model in the PolyUMod library. It creates each of these models, and it creates a lookup table kind of interpolation based on temperature, similar to what Abaqus and Ansys, for example, do in multiple temperatures. If you have a set of parameters for each temperature, you can combine them and get the temperature-dependent version of that model. You can also do that here using this feature. If you do that, you get predictions like this. Here's my new model, has all these parameters, and it can interpolate between the different temperatures. You set what each of these tests are by these temperatures here. So if I say this is 200 and this is 300 degrees Kelvin, for example, I can see if this ends up being temperature-dependent model by adding data at different temperatures and see what the prediction looks like. So I'll do that by, I'm going to turn off this, and I'm going to click on this virtual test case. So these are virtual experiments, like what if kind of experiments. So I'm going to do uniaxial tension, 3 temperatures. So I pick this one. We end up with 3 test cases with 3 different temperatures. If we run that, we'll see that our now multi-temperature model indeed gives different response at different temperatures based on all this. And then if you have a multi-temperature model, the last thing I will talk about here is you can also divide it up into individual temperatures again by going to extract PolyUMod multi-temperature models. If you click on that, it extracts each of these temperature models into files that you can open separately. So I'm going to close this and we'll see if we can find these files somewhere. So we'll go to, here they are. We got these two files that contain these models at multiple temperatures. So that's useful. This is somewhat not so important, but maybe useful to know about a feature that we added, that if you open a new window and you go to File, Run Validation Tests, what it's doing, it runs a few quick tests internally to see what the predicted stress values are for some material models, and it compares that to known values in a database. So that's been hard-coded. So this is a way to make sure that the software works properly on your computer. So we use this sometimes to verify that it's been implemented correctly. And we'll continue working on these as we move forward. But this is a quick way to see that it works properly. We have a number of new native material models, which are always nice to have new native material models. I'll talk about that. I guess I can just do it this way. I'm going to open an exemplar file here. So here's an exemplar file. And let's start talking about the Ansys linear elastic with creep. So this is a model that you could calibrate before with the previous version, but now in our new version, this becomes super quick. So if you go under Ansys for material models, you can say linear elastic with creep. And there are a number of different creep models you can pick here. The one I like the most is the strain hardening model. So I've picked that one. And here are the parameters. So just click once. Here is now, you see they took 100 milliseconds to calculate this because all the calculations are done internally now. That's what native model means. Otherwise, in the past version, MCalibration had to call Ansys. Ansys had to start, run, extract the data, and then read it into MCalibration. All automatic, but it took many seconds. So now we can run this very quickly. We can calibrate this model in very quick time. See, all these attempts happen in a fraction of a second. So that's a new material model that's available, the Ansys model with creep. We have the Altair Bergstrom Boyce model as well. So at the bottom here, we're starting to implement Radioss material models. You can pick this one. And if you run that once, you'll see that, okay, this is not the best value, but it runs really quick. So we can calibrate this one without much effort, which can be useful. We have a COMSOL yaw hyperelasticity with linear viscoelastic and Mollins damage, which is an interesting combination of things. That's also a built-in feature that works very well. I'm going to not demonstrate that, but you can play with that if you're interested in COMSOL material models. The last feature I will talk about is an interesting new idea that we're working on, which is something called Abaqus cohesive elements. So some of you are familiar with cohesive elements, and some of you have struggled to calibrate them in the past. So I'm going to try to demonstrate how you can use MCalibration now to do this. It turns out that it's quite easy to do with the new features that we have. So to start, I want to show that if you're interested in this, you may want to, well, let's do it in a different way. Let's do it from within MCalibration. So I have a experimental data file here. So when you work with cohesive elements and cohesive contact surfaces in Abaqus, you need to specify to Abaqus some interesting material parameters. Let me just actually show you what they look like typically. Here's a already calibrated cohesive model. It has these types of commands. We have star elastic type traction. We have the normal and the shear stiffnesses. Then you have damage initiation. You have a lot of options for what they should look like. Here is the normal stress for damage initiation, and it's the shear stress. Then you have damage evolution, the different types of options there. The best one I like is the tabular option that's given here. And then you can add other features in the end in terms of multi-axial behaviors. And then down here is also listed the corresponding cohesive model for surface interaction. So this file was automatically generated by MCalibration. And MCalibration can give you all of these values very quickly. So that's what I want to demonstrate now. So I'm opening up a new MCalibration window. I go to Calibrate. I'm going to select my cohesive element model first. So set material model. In this version, we only support Abaqus cohesive elements. We will support Ansys and other finite element versions in future releases, but this is the one we have implemented first. Here it is. And it doesn't have much text, but it has a link to an article that I do recommend that you read if you are interested in this. So here is the link that opens if you click on that one, and it's Calibrate Abaqus cohesive models with MCalibration. So you can take a look at this if you're interested in how this works in more detail than I will go through here. I'm just going to say OK. And here is our set of parameters. And I need to read in the experimental data here. So I'm going to say add experimental data. And I will load my experimental file. So again, I need to find where this was. It's under webinar. It's under cohesive elements. It's experimental traction separation data. So this is interesting, right? When you work with cohesive elements, you specify not the stress strain response of the adhesive. You specify the traction separation response. So traction is another word for stress. And separation is another word for displacement. So you input the displacement stress data, basically. But in MCalibration, you still use an experimental data option here that uses, in MCalibration language, time, stress, and strain. So strain is really interpreted loosely here as displacement. And that is OK, because in Abaqus and most FE codes, typically what you do, you say that the adhesive layer has a unit thickness. So therefore, the displacement will be the same as the displacement anyway. So that's a convention that's typically used, and it's discussed in great detail in the Abaqus manuals if you're interested in that more. So I read in my data here. Here's the strain and the stress, which is traction and separation. You see, you pull on it, the adhesive starts to fail. It fails in a certain way, and then it ultimately is just gone. So this is the damage evolution part, and this is damage initiation part. So we're going to work with this data. To set this up in MCalibration, there are a few things you need to do, which is not so obvious perhaps. That is, you should specify true stress, true strain, and you should specify the loading mode to be confined tension. It's also called confined compression here, but it's the same thing as confined tension. Of course, the adhesives are very thin typically, and in fact, cohesive element models that I'm talking about are 1D in this case. So it's a 1D deformation, and we use confined compression, confined tension as the loading mode. Once you do that, you have the curve here. The graph says true stress, true strain, but you should think of it as traction separation. And here are the parameters for the cohesive model. Are these good parameters? We don't know. Let's try to run once and see what it looks like. We'll see that's really terrible, right? The prediction in blue is much higher than the experimental. So we need to fix these a little bit. We could calibrate from here, and they will do it for us. But we can also be a little smarter about it and try to do this manually a little bit. We'll see that the modulus of this cohesive model that we have here is way too stiff. So I'm going to make it 100 times softer. So I'm going to make it 10 MPa. Stress initiation is where does this curve roll over? It's not 100 megapascal, it's about 1. So I'm going to make this 1. Then I run again. And that was pretty good. That was a pretty lucky guess, I guess, that the blue curve now is the model in MCalibration. And the red one is the prediction. There are some few additional things here. And if you read the article I mentioned, there are some things you can learn about this. But this E is the stiffness. That's the slope of the blue curve. That looks pretty good. That's something we can have the software optimize that though. So we leave that as optimized. Max separation is how far can this adhesive be pulled before it fails? So 0.5 gives us this response. If I make this 0.3 and I run one more time, you see that it goes up here and then it drops faster. It can only take a certain displacement before it fails. So 0.3 is another value. It's a little too fast drop, right? Well, we can have the software find what the best drop is. So I'm gonna allow the software search for max separation, because we can get that. Of course, our data here goes all the way to failure, so that's a good idea. The stress initiation is where this stress starts to fail. The material starts to fail. This is too high. One can argue that the initial response is linear elastic, and then it starts to soften here. So the actual onset of damage should be around here somewhere. So if I click on the mouse, it says 0.66 here. So I'm going to make the stress init 0.66. And then I run one more time, and it looks a little bit like this now. But we can let the software figure out what this value should be. We don't need to do that. And these values here, the delta values, are spline points that represent the curve here. So there's a certain number of spline points that capture this response. And this number of terms is how many points in the table in the end are exported. So this is good enough. I'm going to now see if the software can help us with this here. I'm going to go slow, careful optimization from this point. So I'll pick that option, and I say OK. And we'll see if it can help us calibrate to this here. See that initiation is a little too high. So this value should be a little lower. Hopefully we'll kind of fix that a little bit. The error is going down very nicely though, and it's kind of to wiggle around to match this data. And if you wait a little longer, it will gradually get better. And I'm still using a very slow, careful calibration as the option here. We could use a more aggressive, faster, converging optimization algorithm, but this one is kind of interesting to look at sometimes. I'm just going to stop this here, saying, okay, this is wonderful. This is the one we like. Once you're done with this, you can then export it, and just export it Abaqus-IMP file, for example. I'm going to call this untitled.inp. There it is. And I will open the file. So here is now my cohesive model that I can plug right into Abaqus and use this in my interfaces and have them fail properly. The one thing I didn't talk about is, of course, how do you get the input to this calibration, which is the traction separation response. If the adhesive, so one hint I will give you, and then we need to stop. We're running a little long here. If your adhesive is nice and soft, like a pressure-sensitive adhesive, PSA, you can just do a tension test on the adhesive itself, or a shear test, or both, or a combination of those. And that gives you good traction separation data. If you have a very stiff adhesive, it's sometimes better to use a slightly different approach based on fracture testing. So that's a little bit outside the scope of our discussion here today. But the idea from those tests is you extract experimentally the traction separation response. Even for stiff adhesives, you can plug it into MCalibration and can calibrate these cohesive models in very short time after you're done with that. So with that, I think I have covered all the things I wanted to go through. We are running a little later than I anticipated. There are a few final comments I would raise, and then what we'll do is we will stop. I will say that I'm very excited to release this version. I think you'll find it useful. If there are features that are missing in this version that you'd like to have, please email us. Please email us at support@polymerfem.com or to my email directly, either way. And we will try to implement them in the next version. We are very excited to add features that people care about. We will certainly add our own features as we move forward. But if you have any features you like, please let us know.